So thanks to Pierre for the very comprehensive summary of the satellite oceanography and the use in operational oceanography, especially for SST concept retrieval basics. So I can skip some of the material and go through some of the material relatively fast. So there are 2 lectures for this, and the overarching title is the satellite sea surface temperature and salinity observations and their roles to constrain ocean models. So first, I would like to acknowledge a list of colleagues that I talked to, including Chelton and Ed Armstrong and Jorge Vasquez from JPL, who are experts for sea surface temperatures. And also Eric Heckert, formerly University of Maryland, who just joined NASA Goddard Space Flight Center. And Matt Martin from UK Met Office, Benoit Chanchan, and Eric Baylor from Benoit from Mecatation, and Eric Baylor from NOAA Seastar, Armin Koh from University of Hamburg. And these are people who have been engaging in satellite sea surface salinity assimilation, either have published or preliminary results. So the outline for today's presentation is listed here. First, I'll describe the importance of sea surface temperature and salinity on ocean processes, Earth's interaction, and water cycle studies. And followed by a description of the advantages of satellite sea surface temperature and salinity and their complementarity with in-situ observations. So Pierre have also elaborated on some of those topics. And then I will go through the give an overview of satellite SST observations, including the 2 main type of observations, which is the infrared observations and the passive microwave observations, and the SST constellation and the need for future measurement of SST and the gap. And then I'll talk about the SST retrieval methods from satellites and the issues for calibration and validation analysis. So I will call it CalVal. Usually it means calibration and validation. Oops. Okay. And then I'll talk about some major issues for satellite SST related to the uncertainty. And then the main portals for the level 4 SST distribution. And finally, I'll talk about the use of satellite SST in constraining ocean models. So this is the outline for tomorrow. I will not go through this in details, except to point out that tomorrow I'll be focusing more on the satellite sea surface salinity, the issues, the retrieval, what's the status of the quality and how good it is compared to the in-situ data, and what are the issues in comparing to in-situ data. It was actually a big issue because of the sampling difference that I will elaborate tomorrow. And then I will talk about the scientific achievement, give some example, future challenges, and the ongoing technology development to improve sea surface salinity measurement from space and the use of salinity for constraining models. So back to today's topic. First, I'll be talking about the importance of SST and SSS on studying ocean processes, interaction, and water cycle study. Well, first of all, SST and SSS determine surface salinity, right? And the horizontal and vertical gradients of the surface salinities are important to mixed layer dynamics, ocean currents, including mixing and convections, and surface salinity are also important for formation of water mass at the surface. So now SST, can you see the pointer if I have this large incident angle? Okay. Thank you. So sea surface temperature is also actively involved in air-sea interaction, right? In particular, it affects a lot of air-sea fluxes, including heat flux, evaporation, momentum flux, wind stress that Mark Barraza talked about yesterday, as well as gas transfer, such as CO2 flux. And also, horizontal SST gradient are important to ocean atmosphere coupling from very large scale down to mesoscale, and perhaps even on some mesoscale, and I'll give some example for that. Now, for sea surface salinity, it does not actively involve in direct air-sea coupling, right? But it affects SST indirectly, and therefore it regulates the air-sea interaction. And I will also give an example of that. Now, finally, sea surface salinities is an important biogeochemical parameters for parameters such as total alkalinity and studies of ocean acidifications. And salinity is also a very important indicator of changes in the global water cycle and studying the linkage of the ocean with the water cycle. So some of the example that I'll give to highlight some of this importance is first, the large-scale SST gradient and ocean-atmosphere coupling. So the example here is the Bjerknes feedback associated with the El Nino Southern Oscillation. So here's the schematic pictures of the tropical Pacific Ocean sea surface atmosphere thermocline depth, and you have the trade wind pushing the cold tongue water towards the warm pool and maintaining this east-west SST gradient. And associated with that is the large-scale atmospheric pressure gradient and the Walker circulation that maintain the trade wind and then push the warm water to the west. Now, if you have perturbation, say westerly wind burst, that weakens the wind and send a Kelvin wave to the other side, which changes the thermocline depth, affect SST. Thermocline, depending the thermocline changing the upwelling. Once you have the change of the large-scale SST gradient, it affected the large-scale pressure gradient and therefore the Walker circulation, and it changed the trade wind, which further depressed the thermocline. It's a positive feedback associated with ENSO. So that's called the Bjerknes feedback, and it occurs in the, to some extent, in the tropical Atlantic and the tropical Indian Ocean as well. So it's an evidence for large-scale coupling of SST gradient and wind. And Mark Barraza yesterday gave a lot of examples for mesoscale coupling of SST gradient and wind, so I'm not going to go into the detail. Just to give one example, this is from Dr. Chelton for this SST and wind coupling associated with tropical instability wave. Essentially, when you have SST, here's a cold tongue in the tropical Pacific. When the wind go from cold to warm water, right? If you overlay the SST contour with the wind vector, you see larger wind vector when it goes from cold to warm water. So one interpretation of that is when you go to warmer water, there's more, the atmospheric boundary layer is more unstable, more particle mixing, draw down a higher level momentum to the surface. So that's why you have larger wind stress and therefore the divergence. But that's only one of the interpretations. So Mark yesterday listed a long list of interpretation. It's always a very active discussion topics in the International Ocean Vector Wind Science Team questions meetings, as Mark mentioned yesterday. So the interpretation of this mesoscale coupling physics is still an area of active investigations. Now, I mentioned that the salinity can indirectly affect sea surface temperature, right? So that's through the effect of near-surface stratification. So here's an example of the time mean vertical temperature gradient. So here's the mixed layer. You have an here's the isothermal layer where you have a near uniform temperature. And here is the salinity profile. And in a lot of regions, tropical regions, where there's a lot of rain, river plume regions, where you have fresh salinity, and there's actually a salinity stratified layer that has no temperature stratification, and therefore the mixed layer is actually, mixed layer depth is more determined by the salinity stratification rather than the temperature stratification. The isothermal layer determined by the temperature profile will be deeper than the mixed layer determined by the uniform salinity layer. And in between is what's called the barrier layer. And the barrier layer actually inhibits the vertical exchange of heat between the mixed layer and the thermocline. And therefore, it affects air-sea interaction because it traps the heat in the shallower mixed layer and amplify the response of the mixed layer SST to heat flux. So this is one example where salinity can affect SST and therefore regulate air-sea interactions. So remember when I introduced myself, I said when I talk about SST, take it with a grain of salt. This is it. Okay, so now salinity as an indicator for global water cycle changes. Now, to study global water cycle, there are many elements, right? Evaporation, precipitation, continental runoff, there's ice melt. To monitor all those mirror elements are very difficult. So we know that large-scale, global-scale EMSPs are really difficult. Not so much for the precipitation part. Precipitation has its issues too, even though we have the satellite, we still miss a lot of things. Snow cloud, for example, that are not well measured by radar. Evaporation is just very difficult. Mark Barassa can tell you a whole story of why it's so difficult to measure evaporation over the ocean, to some extent over land as well. Now, monitoring global river discharge is even more difficult. There are so many rivers, and many rivers are being dammed, by humans. So it's very difficult to quantify the changes associated with continental runoff as an indicator for global water cycle changes. Sea ice melt, that's very inhomogeneous as well from both poles and require a lot of good measurements, and in fact, sea ice thickness is not well measured for the thinner sea ice, which I'll discuss tomorrow. So given this, seasurface salinity is a direct response to all these elements, EMSP, continental runoff, and sea ice melt, so could potentially provide a very good large-scale, low-frequency indicator of changes of the global water cycle. So here's one example from the work by Paul Durack, Susan Weifel, and other Australian colleagues. And so they look at the historical near-surface salinity data in the past 5 decades. And first, if you look at the time mean E-P pattern and the SS pattern, they have some large-scale resemblance. So decades ago, there was already suggestion that sea surface salinity could be a rain gauge. But I would like to caution you that they only work on some very large scale and very low frequencies. On the smaller scale and shorter time scale, ocean dynamics is really important. And so, but given this resemblance, and then they look at the trend of sea surface salinity from the historical data, which is shown here. So now you notice that it mimicked the time mean salinity pattern, which is blue, blue, red, and red. And if you plot the scatter plot of the change of salinity, the trend of salinity versus the time mean salinity, let's see. Time mean salinity versus change of salinity, you see a relation which says that the salty water gets saltier and the fresh water gets fresher. So one possibility of that to happen is that the evaporative region is evaporating more, and the rainy regions is getting more rain. So wet getter, and dry area gets drier. So that's the scenario for a possible acceleration of the global water cycle. But this is an area under active debate. If you ever go to the GWAX meeting, the hydrologists will basically say that this is only over the ocean, that they did not find this over land. Perhaps it will affect some regions where it's actively linked to the evaporative region over the ocean that provide a moisture source to affect land, but perhaps not over the entire all the continents. So that's something that's need further studies. So as I mentioned just a minute ago, that in the subtropical high salinity regions, these are areas where it's dominated by evaporation. So those are main source of moistures for rainfall over land in certain regions. So in fact, the Woods Hole colleagues, Lai Fang Li, formerly at Woods Hole, now in Duke University, and Ray Smith and other Woods Hole colleagues, they have a couple of recent papers using the subtropical salinity as a predictor for rainfall in Sahel. This is one paper published in Science Advance, and another one in Journal of Climate for predicting rainfall events on the US Midwest. So this is just one example for the Sahel rainfall predictions, where they show the importance of prediction for a list of predictors: subtropical Atlantic sea surface salinity anomaly, PDO index, Mediterranean SST, They also look at local SST in the subtropical Atlantic as well. Atlantic multi-decadal oscillation, Nino 3.4 index, Atlantic Nino index, SAOD, I forgot what this is, Indian Ocean. Perhaps this is a Southern Ocean index. And this is also an Indian Ocean index. So the upper part shows that without the salinity, or the lower part is showing the prediction without the salinity. The upper part is with the salinity. So you see quite a difference in scale. The upper part has the R square larger than 0.5, and it's a significant. And down here, it's less than, significantly less than 0.5. And over here, you see the salinity is being the best predictor for the Sahel rainfall. And so in the paper, they also describe how this works. It essentially has to do with evaporation and then atmospheric moisture transport. Once it got to land, it rained, wets the soil, and then the soil moisture feedback changed the pressure gradient between the Sahel regions and the Mediterranean region, which draws more moisture from the Mediterranean into the Sahel region. So a similar mechanism worked for the US Midwest, where the soil moisture feedback affect the pressure gradient between the Gulf of Mexico and the US Midwest, which draws more moisture from the Gulf of Mexico. So it's not so much just the evaporation from the subtropical Atlantic that is completely providing the moisture source, but it's triggering a soil moisture feedback, which draws more moisture from other area in the ocean that help improve this forecast skill. Now, you may ask, if it's evaporation, why don't we just use SST from the subtropical Atlantic, right? Well, again, Mark Barraza can tell you a lot more about why it wouldn't work, because evaporation does not just depend on SST. There's air temperature, there's humidity, there's wind speed, there's a long list of other things, and it's very uncertain. But sea surface salinity there on large scale and sea surface time scale respond directly to E minus P, and therefore it's a pretty good indicator of the evaporation. So that's the gist behind this whole prediction scheme. So now the second topic is the advantage of Satellite SST and salinity. First of all, the Satellite SST and salinity, they have a systematic ability for synoptic measurements of smaller scale high frequency variability in the ocean, which is important for cross scale interaction, smaller scale high frequency and the interaction with larger scale and lower frequency. So that's quite important. And secondly, satellite observations have generally more uniform space and time sampling, which enables the calculation of gradients, salinity gradient, temperature gradient, and therefore density gradient, that are important to study of frontogenesis, eddy mean flow interactions, as well as biogeochemistry. Fronts are important for biogeochemistry. And the satellite data also have good coverage, often global, and they cover marginal seas and coastal oceans where in-situ data are often sparse. And so that large-scale coverage is also a major advantage for studying teleconnection, global teleconnection, or interbasin teleconnection. So these are some of the advantages of satellite observations. But like PRE, I want to emphasize the complementarity between satellite and in-situ observations. In fact, the surface information from satellite and subsurface data from in-situ measurements are important in inferring the four-dimensional structure of the ocean. And also in-situ measurements, such as those from Argo, mooring, and ship-based measurements, they are important for calibration and validation of the satellite observations. And in particular, the high-frequency mooring measurements, they help the alias diurnal cycles that are not well captured in many of the satellite measurements. And Mark Barraza yesterday elaborated on that in the context of wind, but the same issue apply for SST, salinity, and other satellite measurement as well. And now, on the other hand, stable satellite sensors could actually help identify drift in situ sensors. There are many examples of this. For example, going beyond this, the stability of the GRACE gravity satellite helped detect drift in ocean bottom pressure sensors. That's one example. And recently, we have shown that the consistent variability between the SMAP satellite and small satellite for sea surface salinity in tropical Pacific help actually identify a bunch of mooring records that have issues, either salty drift or fresh drift. So we reported that to the NOAA PMEL folks and the National Buoy Data Centers, and those data have been there for 2 years. And so they looked into it, and then they found that some of the moorings are actually fouled, biofouling. But there are some that might have been cracked chambers, somehow the connectivity sensor got water into it or something, because the drift goes either way. So they're still trying to figure out what happened to those. But once they received our input, they went back and they fixed the record, those data. So those are actually quite important for operational oceanography. If you're downloading this near real-time data from the Tropical Buoy website, and if you have those sensor drift, they need to be removed. So unfortunately, the near real-time processing of this mooring salinity data is not quite up to date, and actually the satellite salinity could help provide that near real-time quality control capability. Now, I'm going to describe some satellite observation of the sea surface temperature. Mainly, there are two types of sensors for SST, as Pierre mentioned. The first type is the infrared sensors, typically a few microns, to 3 to about 10 microns, or beyond. It's the thermal infrared, and a little bit shorter is the near infrared. And there are many examples. The longest one is the advanced very high resolution radiometer, the AVHRR, on board of the NOAA series satellite. That's like a single wheel radiometer. And then the ESA has this along track scanning radiometer, ATSR, followed by the advanced ATSR called AATSR. So this is a scanning radiometer that provides multiple wheel, and it's very accurate measurements and very good internal stability. And so it's a major advance in terms of the in terms of the infrared measurements. And NASA has the MODIS, and also there's the VIIRS, that's visible infrared imaging. And more recently, there's the, following the AATSR heritage, ESA has the SLS-TR on Sentinel-3 for infrared measurements. Another class is the passive microwave measurements. So examples are the NASA's TRIM microwave imager, normally called TMI. So TRIM is the tropical precipitation missions, but the microwave imager can also be used to retrieve SST because it's in the C-band frequencies, which has good sensitivity for sea surface temperature. And then there's the polarimetric microwave radiometer for US Navy's WindSat. It was designed to measure wind, but actually the sea surface salinity product from WindSat, it's pretty good. And there's the, after that, there's the EMSR, the Advanced Microwave Scanning Radiometer on JAXA's RDOS, followed by the EMSR-E on NASA's EOS Aqua satellite, and the EMSR-2 on the JAXA's JCOM W1. And more recently, NASA has the another precipitation mission, Global Precipitation Mission, GPM, they have the microwave imager. If that's 10 gigahertz, a bit higher frequencies, that's also good for measuring SST, although it's not as optimal as the other microwave, which is 6.9 gigahertz, providing more accurate SST measurements. So these are the two main type of SST measurements, and we have a very impressive international constellation of the SST measurement. This is an example for the polar orbiting satellites, so I'm not going to go through this. And next, these are the geostationary satellites. And so it all looks great, and very often SST is taken as a given, taken for granted that it's going to be continued. But as Pierre mentioned, that if you look at the microwave SST, that see-through cloud, I'll elaborate on that a little bit more. There's actually an issue here. A year back, there was a really critical discussion for the continuity of the microwave SST with the 6.9 gigahertz channel, like the EMSR type, because that gives more accurate measurements of sea surface temperature than the 10 gigahertz channel on GPM satellites. So the continuity of that from ENSO E and ENSO 2 and onward, it's quite important because it sees through cloud. Let's see. Last week we just heard. Well, rewind a little bit. So the international community has been engaging JAXA, Japanese government, to try to convince them to continue this. And the GCOS, Goose Ocean Observational Vision for Climate, OPC, co-chaired by John Wilkin, we sent a letter to JAXA, and we just got a response last week or 2 weeks ago. JAXA said that now the Japanese government have put in the development money for FY18 for this. So that's good news, and hopefully there will be money for going into phase B and phase C and operation. So now some pros and cons of the infrared and microwave sensors. So for infrared sensors, the advantage is that it's got a long heritage. It's got decades of data, which is really important for studying multi-decadal variability and deciphering natural variability versus anthropogenic change. And it's got a high spatial resolution as well. It's down to 1 kilometer. And it has good temporal resolution as well for the geostationary satellite, some 30 minutes to 1 hour. And it's generally more accurate than a passive microwave radiometer. But the disadvantage is that it's obscured by cloud. It was a big issue. So during my PhD, I used a big electronic digitization board connect to a monitor and hand digitize some 10 years of infrared images, 2 images per day for the Gulf Stream North Wall positions. The cloud is just so difficult to work with the infrared images to make a continuous North Wall position of the Gulf Stream. And another disadvantage is that the infrared signals are significantly contaminated by atmospheric effects such as water vapor and aerosols. So in fact, if a volcano, it's going to be a volcano eruption, there's going to be a big impact on the SST, even on very large scale. And so those are particularly true for single view sensors like AVHRR, but better for the spinning AVHRR class of sensors. Now for microwave sensors, the advantage is that it sees through cloud. That's why we need the continuity of the microwave sensors. And it's relatively insensitive to atmospheric effect because of the much longer wavelength and lower frequency. So aerosol is not really a problem for microwave. But the disadvantage is that it has low resolution. So typically it has 25 kilometer resolutions for the 6.9 gigahertz channel. And for the 10 gigahertz channel, we got about 10 kilometer resolution. It also have lower temporal resolutions as well, typically covering the entire ocean, every 2 days or so for one sensors. But it's affected by surface processes, rain and surface roughness from the ocean surface, as well as radio frequency interference. So those are factors that need to be removed in the retrieval. Now here's an example of the infrared images and microwave SST images. So you see that the cloud, so this is during the February, a few days during February in 2000. So you see that there's a lot of area that are obscured by cloud for SST. So in fact, for operational oceanography, this is a big issue. A combination of those will be really important for operational oceanography. And this is also one example for the comparison of the infrared and microwave SST in a scatter plot against buoy SST. So you see a larger spread of the microwave SST versus buoy. And this is just one example during a few months period in 2000 during summertime from Gary Week. And so these numbers here are the RMS is a 0.76 for infrared and 0.9 for microwave SST just for this period. And in fact, the overall, if you look at the literature, the overall accuracy of the infrared SST is about 0.3 degree, where the microwave is 0.5. So the infrared is still better accuracy than the microwave SST. Now, retrieval and care well issues. There are mainly two retrieval methods for satellite SST. The first one is an empirical retrieval. So typically, a nonlinear multiple regression is formed by determining the coefficients of the signals from different infrared channels with respect to the in-situ SST data, and that includes an offset, which is the bias. So once you determine those coefficients, and when the more data come in, and you just use this regression to derive the SST retrieval. So in doing so, you actually effectively remove the bias to a larger extent, and because it's empirical regression, so it tends to be, that's one of the reasons that it tends to be more accurate comparison, and in fact, some of the in-situ information is already built into the regression. Now, for another method is the geophysical retrieval, which uses a model, radiative transfer model that PRE have described in some details. And so you take that model, essentially you correct for the atmospheric effect and then and the surface effect, and then you can get the SST retrieval. So that's typically more challenging for the infrared data because the atmospheric effect for the infrared data is a lot stronger than the microwave SST. And so that method is typically used for microwave SST retrievals. Now, the infrared and microwave SST, there's a relative bias. So that's important in that need to be taken into consideration in data blending and in data assimilations. So the infrared sensors measure the top microns or so of the sea surface, whereas the microwave sensors measure the top millimeter. And this relative bias could be very important for long-term studies, and in particular, say the Reynolds OISST, if you go to the website, right, there are two products. One is the AVHRR only. The other one is the AVHRR plus the ENSO. If you're looking at a longer-term trend, do not take the one with the blended AVHRR and ENSO. Despite the effect of the bias correction, there are still some residual difference there. So if you're looking for delicate multi-decadal signal, you need to be very careful. So the stable system sensors are very important for looking at long-term SST trends. And so the processes that contribute to this kind of difference include the diurnal heating and evaporative cooling that are not well measured and not well understood. But there has been a lot of effort for this bias correction in SST blending as well as in data assimilation. So one example for data assimilation is a UK Met Office from NEMO-VAR system that correct for the SST bias before they assimilate. And in fact, now they're doing it for the salinity as well, correct the salinity bias before they do the assimilation. Now the GRIS SST project, PRE have also mentioned, this is a really great resources for high-level SST product, blended infrared, microwave, and many of them have in-situ also. And they have also various ways to characterize the uncertainty among the different satellite products. This group of products are the ones that provide some kind of uncertainty information for the SST data. So it's really helpful for understanding the consistency and error characterization, as well as to factors contributing to the difference. And this data can be downloaded from the NASA Physical Oceanography DAC at JPL, PODAC. And if you want to know about the tools and different way to download the data and do analysis online, I will show you separately. Now, the major issue for satellite SST is in the high latitude. In fact, tomorrow you'll hear that it's the same thing for sea surface salinity. And here's an example for comparison of the high latitude SST product with buoy data from in the Arctic Ocean. This is time, and the different color curves are from the different GRIS SST product and one ensemble global multi-product ensemble GIMP. And the black is the buoy data. So you see a large spread, and many of them, these satellite product are below the buoy. So there's really an issue here, the consistency and accuracy of the even the high-level branded SST product in the Arctic. On the right-hand side is a comparison with a single sensor retrieval. And the blue is based on WinSat SST. And the red is, I believe, is from MODIS. I think this is a Navocean retrieval. And so you still see large difference between the two, although the red, which is based on the MODIS, tend to be more less biased compared to the WinSat SST. And if you go to that GRIS SST website, every day it has a multi-model ensemble for some 12 products and the spreads. So it keep updating every day. That's why it's a very good resources. So before I left for the trip, I just grabbed one. That's for September 27th. And this is a spread among different products. And I zoom in into the polar ocean. So you see very large discrepancies in the Arctic Ocean and to some extent in the Southern Ocean as well. So this is one of the areas that it need to be improved. And for microwave SST, definitely atmospheric effect related to surface roughness, and for infrared SST, there are some additional atmospheric processes related to snow cloud that may need to be taken into account. I'm not the expert on that area, but it's an area of active research. Now, use of satellite SST for constraining ocean models. And in fact, most ocean models now use SST to constrain the state estimate, or use the derived state estimate to perform either mesoscale ocean forecast or seasonal to interannual forecast of the couple ocean hemisphere system. So there are two websites here that are listed. One is the Ocean Synthesis Directory and the reanalysis.org that has various ocean analysis system and description. And I believe the Godae website has a somewhat similar list too. But I think you have to go into the document instead of click on the link and show the data being assimilated. Essentially, when you click on the link of every system, pretty much every system has SST in it. But not just SST, it's usually a suite of other data that are assimilated together. So what are the effects of the SST assimilation on models? Well, it constrains the temperature variability in the mixed layer, and it also help compensate for surface forcing errors, in particular the surface heat flux. And in fact, in some systems, such as the ECHO, or estimating the circulation and climate, or the ocean that use 4D over the entire model trajectory, the SST data, along with other data, are very important for constraining the surface forcing, not just the heat flux, the wind as well. Remember the Bjerknes feedback example that I showed that the SST gradient are coupled to the wind. So if you have the wind wrong, your SST gradient will be wrong. So having SST data will be important not just to constrain the heat flux, but to constrain the wind as well. And also in the ECHO context, it's also used to constrain the vertical mixing. If you don't optimize the vertical mixing coefficient and you blame the error onto the heat flux, you could have incorrect error compensation, because ocean model do have error, especially in the mixing. So it's important to correctly ascribe the error associated model mixing versus the error associated with the surface forcing. Now, I mentioned that SST are typically assimilated with, in combination with other data sets, and that is to ensure more balanced constraint. And in fact, there are various publications that shows that additional data used in the system generally improve the fidelity of the model state estimate. So here are a few highlights of the assimilation of SST in improving model. And this one is actually a combination of a Salinity from Aquarius and AVHRR SST from the Indian colleagues. In the top, it shows the surface current, speed and vectors. Sorry, this is the actually the EUF pattern from the surface current, not the timing current. The EUF from the surface current from the model run without data assimilation, and with assimilation of the Aquarius Salinity, and with the assimilation of Aquarius Salinity and AVHRR SST. And this is from the independent estimate based on satellite observations and wind of sea level and wind, and this is the OSCAR ocean surface current product. So you see that the initially the model without data assimilation is really exaggerated. This current in the tropical Pacific, and it underestimates the current in the tropical Indian Ocean. So as you add the data, it progressively gets closer to the observations. And they also have a more quantitative description of the impact. And again, here are the 3 runs, the control run without control run, and then the Aquarius assimilation, and then the combined Aquarius and SST data assimilation using 4 different criteria. One is the spatial correlation. This is with respect to surface current. Spatial correlation, temporal correlation, spatial RMS, and temporal RMS. So for all of this, essentially the bottom line is that there's a progressive improvement, both in correlation and in RMS error of surface current as you add the data, salinity and temperature. So now here is one example from the Japanese syntax F couple model forecast, where the only data that they assimilate is SST. And in fact, it's a relatively simple scheme. It's essentially nudging SST in the couple model, trying to constrain the coupling. And yet it was turns out to be quite effective and showed a good impact on several forecasts, one of that being the ENSO forecast. They also look at the Indian Ocean dipole forecast and global precipitation forecast, and all of those shows improvement. And here the example shows the time series of the Nino 3.4 SST observed in black, and the different color curves are the hindcast, I should say, not forecast, with different lead times. So you see that it's looking quite good if you have seen these ENSO forecast forums with different models, and this is pretty good. And the lower 2 plots are the anomaly coloration and RMS difference with respect to Nino 3 SST. The dashed curve is the persistence that you have to beat in terms of forecast skill, and the other curves are the forecast with a different lead time. So you see that it's significantly better than the persistence. I actually tried to find examples of the impact of SST on operational ocean forecast, especially impact study for withholding SST data, and see what happened. But I haven't quite found it. One of the reasons is that SST observing system is often taken as for granted. So that usually you do that kind of system to justify health advocate for a certain observing system. But that's for SST, we don't have much of those demonstrations. So I unfortunately was not able to find it. The only study that I found is from Jim Cumming from NRL that used the joint method to look at the impact of SST on 48-hour forecast in the Navy system. But that's a combination of both in-situ SST, including Argo, and the satellite. So it's not clear that that impact, whether it has to do with the in-situ SST or satellite SST. So that's why I didn't highlight it here. Okay, so to summarize, so satellite salinity, SST and salinity are important to research in ocean dynamics, as well as ocean biogeochemistry, air interaction, and water cycle studies. And satellite temperature and salinity have unique advantages from space. As I mentioned, a few of those: coverage for studying teleconnection, covering marginal seas, coastal oceans, and the sampling that helps with estimation of gradients and fronts. And satellite SST and salinity are also complementary to in-situ observations by linking the surface and subsurface information. And in particular, tomorrow I'll talk a little bit more about the salinity part, which is a new discovery after the launch of the satellite, and that promoted some specialized sensors to look at near surface salinity physics. And some of you are actually involved in that kind of research, Jesse Anderson from University of Washington in particular. And now we have, there are 2 types of satellite SST sensors, the infrared and passive microwave. They have relative pros and cons. The important take-home message is that AVHRR have good spatial temporal resolution and tend to be more accurate, but infrared SST sees through cloud and have lower resolutions. So that's the main thing that we need to remember. There's a comprehensive, very impressive international constellation of the satellite SST, but the continuity of the most important microwave channel, which is a 6.9 gigahertz channel, that gives the most accurate microwave SST. The continuity of that need to be ensured. So we need to continue to engage COS and engage the JAXA to make sure that this will go on to GCOM W2 and beyond. In terms of satellite SST quality, the most critical issue as identified by the GRIS SST community is the high latitude SST, especially in the Arctic Ocean. And in fact, in the satellite salinity community, we just realized this issue as well. And it's actually contributing to the quality of the satellite retrieval. Because when you move to the polar ocean, where the L-band signal has very little sensitivity to salinity, the sensitivity to SST actually becomes bigger. And yet, the SST quality is not very good, so it has a bigger impact on the satellite salinity retrieval. So improving SST in the Arctic Ocean will also help improve the salinity retrieval. And GRIS SST is a great resource to look at the consistency of different SST products. And I encourage you to talk to the GRIS SST expert to look for, get advice on which product you should use for your particular application. There's so many of them. Satellite SST are used widely to constrain ocean models and improve forecasts, and they are often used in combination with other observation, and that's very important, demonstrating the synergy of different observing systems to constrain model both for operational oceanography and for initializing seasonal interannual forecasts. I'll stop here. Thank you.
Thank you, Tony.
Any questions?
Any questions?
In one of your slides, there was that there is inconsistency in the Arctic region. So that was showing the annual cycle, I guess, in days of a particular year. So that inconsistency was bigger in the earlier periods of the year, like in the summer months, not that much big in the autumn or winter. So is it the seasonal behavior that is causing the inconsistency in the other measurements?
So your question is the seasonality of the discrepancy among the different SST products in the Arctic Ocean, and whether it depends on region as well. So if you, actually I don't know about the dependence on the seasonality, except that this is in the fall. This is SST images. So you see that at this time there are still large discrepancies of them. So based on my limited knowledge of the SST retrieval, I think there are several factors that contribute to it. Surface roughness is one for microwave SST. There might be snow cloud effect on infrared retrieval. Potential sea ice contamination. I'm not sure if there are leakages of sea ice signal from the side lobe of the antenna into main beam where you're looking at the ocean. If that's the case, that could contribute as well. So that also calls for better sea ice measurements, sea ice brightness temperature measurements, so that one can remove that effect in the microwave SST. And if those factors are seasonally dependent, then there will be a dependence of the discrepancy on seasons. And it's a good question for me to follow up with the GRIS SST community. Thank you for the question.
Thank you.
Thank you. Actually, I have a similar question about comparison of infrared measurements with buoy measurement. Because at the low temperatures, the correspondence was very good, but at higher, the spread increased. So why is that?
Say that again. You're referring to this graph?
No, the buoy measurements.
So what about the buoy measurements?
Comparison with infrared.
Mm-hmm.
There was dependence on the temperature. For low temperatures, the correspondence was very good. But with increase of the temperature, the spread of infrared measurements was increasing. It was before, not in this slide.
So your question is the dependence of the consistency of satellite versus SST as a function of temperature.
Yes.
I myself have not looked at that. Yeah, it's another issue that I can follow up with the SST expert to see how it depends on the temperature. But the range of it's actually related to the seasonality. Yeah, all right. So summertime versus wintertime temperature in the Arctic Ocean.
You said it was only 2 months measurement, so there was not much seasonality.
Oh, yeah. So in that paper, they actually conducted a lot more comparison than that. Yeah. So in the paper by Castro, Sandra Castro, Gary Wick, and Mike Steele. So I just picked that example for graphic example for inner comparison. Okay. Yeah. Perhaps you can follow up and look closer to that paper for other plots of comparison in other area and seasons.
Okay, I will. Yeah. Thank you.
I have a different question. Remote sensing of the atmosphere allows to provide the vertical profiles of the temperature and moisture. Is there a way to go beyond the SST in the ocean measurements with the satellites? Below the SST, deeper.
So to go beyond, could you repeat your question? Sorry.
Is there a way to measure with the remote sensing something that is under surface of the ocean? That's what I'm...
Oh, to below the surface?
Below the surface, yeah.
Right, so that's a question of wavelength and frequency, for example. So
this is done in the atmosphere, that's why I'm
typically, asking. Right, so typically they're profiling. That's a great challenge for oceanography because the ocean is opaque to electromagnetic wave in general. So other than barometry that you could use to measure the ocean mass, and altimetry where the sea surface could actually have some correspondence to, say, the thermocline in the variability in the tropics. And so that's not a direct measurement, it's an inference. But the GRACE is a bit of a more direct by measuring the gravity. Other than those, there haven't been it's been difficult to measure the subsurface ocean structures from satellites. So the lowest frequency that you could measure is, say the L band, it goes to about 1 centimeter. So that's still the ocean surface. Yes, if we could do that, that will be great. There is ongoing technology development of using LiDAR to look at the infer mixed layer depth. That concept has been around for 2 decades, and there's some renewal effort for doing that. And there's some new effort, is it called SWAMP? Pierre can help me with that. These missions, satellite missions, that can probably provide measurements of integrated currents. So it's not, again, it's not profiling, more of an integrated quantity. Yeah, I wish we could do profiling of the ocean like we did for the atmosphere. That would be great, but unfortunately, the ocean is opaque. Yeah.
All right, thank you very much, Tony.